Have you ever rubbed a balloon on your hair and seen it stick to the wall? Or wondered why two electric charges attract or repel each other? Most students memorize formulas but don't really understand what is happening physically. In this video, I promise you one thing. By the end of this video, electric fields will stop feeling scary. We will clearly understand Coulomb's law, electric field intensity, electric flux density, Gauss law. Step by step, very slowly, very clearly. Perfect for beginners, GATE aspirants and engineering students. So grab a notebook, relax and let's start from the basics. First is Coulomb's law, the starting point. What is Coulomb's law? Before electric fields, we must understand electric force. Coulomb's law tells us how two charges interact. Let's imagine two charges. They are kept some distance apart. Now two things happen. They attract or they repel. Simple rule to remember. Like charges repel, positive with positive or negative with negative, and unlike charges attract, positive with negative. This is similar to magnets, right? So what is Coulomb's law? Coulomb's law states that the force between 2 point charges is directly proportional to the product of magnitudes of two charges and inversely proportional to the square of distance between them. So mathematically it is given by F is equals to K Q1 Q2 upon R square. Don't panic. Let's break it down slowly. F is the force between charges in Newton, Q1 Q2 magnitude of charges in Coulomb, R is the distance between charges in meters, K is the Coulomb's constant, where K's value is equals to 1 upon 4 pi epsilon 0. What does this formula tells us? Let's understand the meaning. If charges increases, force increases. If distance increases, force decreases very fast because r square. So distance matters a lot. That's why electric force is strong only at short distances. Very simple example. Suppose Q1 is equals to 1 Coulomb, Q2 is equals to 1 Coulomb, R is equals to 1 meter. Then F is equals to K into 1. So force is maximum. If distance becomes 2 meters, F is equals to K by 4. See, distance doubled, force become 1/4. Now our next topic, electric field intensity, which is force without touching. Now comes the most important idea. Why do we need electric field? Question, does a charge feel force immediately even if no other charge is touching it? Answer is yes. That means the space around a charge is spatial. That space can apply force. That spatial region is called electric field. So definition of electric field intensity is force experienced by a unit positive charge. Mathematically, E is equals to F upon Q, where E is the electric field, Newton per Coulomb or volt per meter, F is the force, Q is the test charge, very small positive charge. Important point, less charge should be very small, test charge should be very small so it doesn't disturb the field. Electric field due to a point charge. Using Coulomb's law, E is equals to K into Q upon R square. So electric field depends upon charge creating the field, distance from the charge. So direction of the field, which is very important for exams. From positive charge, field goes upward, outward. Towards negative charge, field goes inward. It is explained with these arrows on screen. So real life analogy, imagine a heater in a room. Heat spreads around it. You don't need to touch the heater to feel heat. Same way, you don't need to touch a charge to feel electric force. Electric field does the job. Now next is electric flux density. field inside a medium. Now let's go one level deeper. Why electric flux density? Electric field depends on a medium. Air, vacuum, dielectric like plastic, glass. So engineers use a new quantity, electric flux density, which is denoted by D. Definition is D is equals to epsilon E, where D is the electric flux density and its unit is Coulomb per meter square. Epsilon is the permittivity of medium and E is the electric field intensity. Meaning in simple words that electric field tells how strong the field is and electric flux density tells how much field passes through an area. Think of water flow. Water speed like electric field, water amount flowing like flux density. In free space, epsilon is equals to epsilon 0. So D is equals to epsilon 0 E. Now the next topic, Gauss Law, the power tool. Now comes the Gauss Law, one of the most important laws. Many students fear this, but trust me, it's actually simple. Statement of Gauss Law states that the total electric flux coming out of a closed surface equals charge enclosed divided by epsilon 0. Mathematically, closed integral E dot dA is equals to Q enclosed divided by epsilon 0. What does this mean? Let's understand step by step. Closed surface is the imaginary surface, sphere, cube, cylinder. Flux is the field lines passing through the surface. Only enclosed charge matters. Charges outside the surface, no effect on total flux. So best analogy, imagine a balloon, air flowing out of it. More air inside, more air comes out. Same way, more charge inside, more electric flux outside. So why Gauss law is useful? It helps us find electric field easily for spherical charge, infinite line charge, infinite plane sheet without complex integration. Example, for a point charge inside a spherical surface, E dot 4 pi r square is equals to Q upon epsilon 0. So E is equals to Q upon 4 pi epsilon 0 r square, which matches Coulomb's law result. Common mistakes students make are, so let's avoid these mistakes that cost marks. Forgetting the direction of electric field, confusing E and D, taking wrong Gaussian surface, assuming outside charges affect flux, not checking symmetry before applying Gauss law. Always check symmetry first. So let's take a quick summary. Coulomb's law. Force between two charges. Then electric field intensity is force per unit charge. E is equals to F upon Q. Electric flux density D is equals to epsilon E. Gauss law, closed integral E dot dA is equals to Q upon epsilon 0. Now your turn. If a charge is placed outside a Gaussian surface, does it affect the total flux? Comment your answer below. I will reply.